You finished it? No? You do the first one? Let's distribute the 5x or add exponents. 5 times 25. I don't know. Get a calculator out. You know? 125. Box of distribution. This is just 3 problems with double distribution. So distribute 6 times, 18 times. 18 multiplications here in these 3 questions. So I'm gonna get it that way. Okay. Yeah, I'm pretty sure 5 times 25 is 125. And this is x to the first times x squared, so that'll become x to the third. I distribute. And then 5 times 5, 25, x squared. And then 5 times 1. That's the first round. Now I will multiply 1 through. That won't be bad. Everything will just stay the same. 1 times 5 and 1 times 1. So we end up with 6. A 2 by 3 gives us 6 terms. And then you combine like terms. So 125x to the third. There's no other third degree terms. Then I'll combine the x squareds. They're opposite, so they just cancel. We're not writing 0x squared or anything. 5x minus 5x also cancels. And then we have a plus 1 at the end. That's the product of that binomial times that trinomial. All of those, and it's just 2 little terms at the end. Third degree binomial. The next one. 3 times 9. Thank you so much. And then that's 48x. And then 64. All right, 2 by 3, a binomial times trinomial give us 6 terms. Combine those terms. 27x to the third. We have a positive 36x squared, negative 3, positive 48 and negative 48. Those cancel. Minus 64. Okay, again, we went from 6 down to 2. Starting to see a pattern here. Something's going on. Now this one is extra tricky. There's no numbers, and there's 2 variables, so probably the most challenging one here. So we got x to the third. We're gonna write x times xy is x squared y, and then x times y squared xy squared. And we'll do it again. Now when I do y times x squared, generally when we start mixing in variables like multiple letters, we'll write them in alphabetical order. So yeah, it's not necessary, but it kind of helps keep things cohesive. So instead of writing yx squared, I'm going to put the x squared first and then the y. Just alphabetical order. And then this is minus xy squared. And then y to the third at the end. So we'll have the third degree. And then I have to match up exponents perfectly. So this is an x squared y, and this is an x squared y. One's positive and one's negative. They're opposite, so they cancel. Xy squared, opposites cancel. And then a plus y to the third at the end. Okay. So obviously there's some sort of pattern here. All three of these problems have a similarity. They're called, these results in these boxes, these are named perfect cubes. Perfect cubes. Perfect cubes are numbers that can cube root. Okay, so we talked about perfect squares a lot, but we haven't really talked much about perfect cubes, but today's all about the cubes. So under your bell work, let's make a list of all of the perfect cubes. Let's do the first 10 numbers to the third power. So make a list of what 1 to the third is, 2 to the third, 3 to the third, 4 to the third, 5 to the third, 6 to the third, 7 to the third, 8 to the third, 9 to the third, and 10 to the third power. You're going to want to get real comfortable with those numbers, just as comfortable as you are with perfect squares, numbers that square root. You want to know numbers that cube root just as well as you know numbers that square root. And then we can talk about fourth roots a little bit. So click on your calculator. How many do you know? Maybe you know the first four. Maybe you know all of them. I don't know. Click them on your calculator, and then make a nice list for sure that you can go back to. Every number to the third power. Because the pattern that's emerging here is something to do with cubes. We got 1 times 1 times 1. 1. 2 times 2 times 2. 8. Anybody just eat that? And then leave it on. Sometime. 7. 2 4 3.
Yeah.
More than 100.
Yeah.
All right, so those numbers are numbers that can cube root. So, pretty much if you're looking at a problem and it has any of these numbers in it, there might be a special way to factor that problem. So today's lesson is about starting with what's in the box and working backwards to the factored form. And it can be a little bit of a brain teaser because you feel like a short problem like this is just a binomial. When you factor it, why does it have to be so long and complicated? But it is. This little tiny problem, 2 terms, factors to 5 terms. Okay, so today we are actually working backwards. You're starting with this, and you have to figure out this pattern. Can anybody just say something about the pattern here? About if you look at this backwards, or the relationship, how we're ending up with 2 terms starting with 6 terms. We need to figure out the pattern and then memorize it. So I'm going to tell you exactly what the pattern is, but if you guys can look and see something on your own, you're better off. I'm just going to make a list here of things that we can observe. Given 2 perfect cubes, that's what those are called. Okay, this is called a perfect cube, 27. And the reason 27 is called a perfect cube is because it's right here in this list. Okay, 64 is called a perfect cube, and the reason it is because it's in this list. 64 is a little challenging because 64 square roots to be 8 and cube roots to be 4. Okay, right here, 125 is a perfect cube because it's in this list, and 1 is a perfect cube because it's in this list. Okay, so I can make more perfect cube problems pretty quickly. I could do 216x to the third plus 512. 2 perfect cubes. I could do 729y to the third minus 1000. Those are perfect cubes. So we're talking about numbers just in that list over there. So given 2 perfect cubes, every time you factor them, it's a binomial and then a trinomial. Okay, that's one thing that we can say right off the bat. All 3 of those problems use a little set of parentheses and then a big set of parentheses. That pattern is there. About the binomial, how is the binomial? Let's look at this one. How are these numbers related to these numbers? Is there anything going on there? Can you see 27 in any of those numbers? Nine and three both have something to do with 27. So the cube root of 27, when I look at the list, is 3. So there's your 3. And then 64, the cube root of 64, when I look at the list, is 4. And there's my 4. Okay? So when you factor 2 perfect cubes, your little binomial here is just the cube roots of these numbers. So we have a binomial, and that binomial is cube roots. It's those numbers in their smallest form. So it's the numbers from the list. The trinomial all holds the same pattern as well. So these 3 numbers are derived mostly from these 2. So 3 squared is right here 9. And 4 squared is right here 16. And what do you think the 12 is? 3 times 4. Okay. So the trinomial is the first number squared, the 2 numbers multiplied together, and the last number squared. Okay. And that happens with all of them. You can look at it here. We got 5 squared, 5 times 1, 1 squared. So that's the pattern in the trinomial. Trinomial is a square, a product, and a square. Okay, so I'm going to let you guys just kind of write that down and think about it for a minute. I'm going to give you more formal notes, and it's actually outlined really nicely in your book. But before I do more, I'm gonna check yesterday's work. Let me just show you what I'm gonna show you here. Here it is. There's a whole there's a whole thing about cube roots here. And I'm gonna outline it really more clearly here. I think it's really clearly. But before we take more notes on it, let's just check yesterday's assignment. We did most of them in class. Here's the answers to the chapter 4.2 on the handout. This is the handout from yesterday. I mostly said whatever you have done in class is good, and then I said, I told my second grade like 5 more. I don't know what I told first grade. How far did you get, actually? How far did you get? This is it? Yeah. So you did a longer than that. I never ever said that the whole handout was required. So I'm just looking, and I know everybody kind of works at different paces. So I just want to see a lot of work done. Some of y'all finished. Good. Put your phone away, Shaylee. The green rest. Okay, so we'll go ahead and scroll down to the 4.3 answers. Does anybody have a question about these answers from the 4.2 section? And here's the answers from the bottom part. The long division, the synthetic, and then the evaluate. You have to go long division. I know you're looking at class. I'm taking questions on this right now. Any questions on this? Any questions on this from yesterday? Maybe you didn't get one, right? You're not sure why? Did you have any questions? Or you can't say it's good? Oh my gosh. Okay, let's get into today's word here, guys. Everyone, you do the pattern. Okay. So the patterns, first off, let's go ahead and take a moment to realize we're now starting chapter 4.4, and it's called factoring polynomials. So we're moving from dividing into factoring, which is the same thing, but if you can't use synthetic division and you're not sure what to do for long division, a factoring method is the way to go. So I'm on page 343, and I'm going to maybe erase this in here a minute. Pretty nice though. Yep, I'm going to start all over. A little bit by a little bit. Alright, looking at page 343. So good. The sum of two squares I never test on in algebra 2. So I'm just going to cross that out. I don't have you factor with I. That's really beyond the scope of what we need here. So when I look at this, these are patterns you should know. This difference of two squares, where we did the plus and the minus sign, we square rooted 36 and 25 plus and minus sign. Notice this is x to the squared, so this is a perfect square. That's not new to you. That's chapter 3. Okay? It's these two that are new. They say the word cubes in them. So it's regarding any problems with these numbers. So now you have to recognize square roots and these cube roots. So I'll go ahead. If there's a minus sign, there's a certain pattern here in signs, and if there's a plus sign, there's another pattern that shows. It's addition and then minus and then plus. So here's two good examples for you. All right, so I'll start with this. If I have a to the third minus b to the third, and my directions just say factor. Just like I've already said, I'll write two sets of parentheses, a little binomial and a bigger trinomial. Okay, a little one, it's a binomial and a trinomial. The binomial is cube root. A cube root and a cube root. And so, same sign is the problem. So this is a minus. So I put a minus sign in. Okay, now, right here, I square the first cube root. So in the trinomial, I'm going to put a squared. Then in the middle, multiply the cube roots together. So in this situation, it will be a times b. I'll put ab here. And in the end, right here, I square the second cube root. So that would be b squared. And you have to memorize the signs. So it's always a mix of signs. If you notice in Bauer Hamlet, plus, minus, plus. This one is minus, plus, plus. They have two different patterns, and the patterns you have to memorize. So this would be minus, plus, plus. You have to memorize the signs. So that's a difference. I'll go ahead and do for any sum, if it's a3 plus b3. It's a binomial and a trinomial. You get your a and your b. You keep the same sign in the middle. But if you start with plus, you square the first, multiply together, square the second, it goes plus, minus, plus. So the sign pattern is different. Plus, minus, plus, or minus, plus, plus. You have to memorize those signs. What's that?
So it really has to be at least one minus.
Always has to be one minus. Thank you for bringing that up. It's so important that there's at least one minus sign here. If you do all plus signs, you'll definitely have all 6 terms remaining, right? The whole reason this cancels just to be 2 is because of these opposites in here. And if you don't have a minus sign somewhere in the problem, you will not have opposites. So worst case scenario is that you put all plus signs in your factors, because when you multiply it out, you'll have all 6 terms remaining. Okay. We've talked about this quite a bit. Let's actually do some problems. That'll help the most, I think. Let's do these ones right here on page 344. I'm going to do just 1 and 3. Is there perfect squares in this? Can I look at that? There's 2 perfect squares. I guess I'll do 1, 2, and 3 here.
I got a question. For the perfect square, that's like plus like a plus b. So the reason we're doing I because at the end of it, it's the cancel out. Like it'd be I squared, which is -1, and then you cancel the 100. Like say there was 100, and it would make it positive. So like 49 squared plus 49, that would be 2n plus 7 squared, and then squared.
All right, so I see 27. I know 27 doesn't square root, so I look at this list. Sure enough, 27 cube roots. So I use a little parenthesis and a bigger parenthesis, a binomial and a trinomial. I noticed that it's a plus sign, which is a sum. So I think about the model for a sum, and I'm going to go ahead and fill in a sign. So signs go plus, minus, plus. Plus, minus, plus. And then I do the pattern. It's the cube roots. So the cube root of a to the third is a. The cube root of 27 is 3. And then I square the a squared. I multiply 3 times a, so that's 3a in the middle. And then I square the 9, 9. And that is factored. Problem is done. I'm going to do number 3 next because it's also 64 and 1 can square root and cube root. So that's pretty fun. The 3 here means I want to cube root 64, not square root it. The biggest mistake people will do is when they see 64, they always think of the number 8. But now you have to know that 64 cube roots to be 4. So I'll do a little parenthesis and a bigger parenthesis, a binomial and a trinomial. I noticed that it's a minus sign. So I'm just going to fill in the signs from this pattern here. It's minus, plus, plus. Fill in the signs next, memorize them. The cube root of 64 is 4, and there's a c next to it. The cube root of 1 is 1. I square 4 to get 16. Square c to get c squared. Multiply 4c times 1 and square 1. And that's the factored form. This one are squareds. This one's a cube, this one's a cube, and then the one in the middle is a square, so. Square root 36 is 6. Square root 9 is 3. So that's 6 and 6, 3b and 3b. I don't know if you guys in this moment can see the difference between a square and a cube, but that's what we're looking at here. Yeah, 4 really belongs more in the last chapter, but it's a square, not a cube. A square is 2 parentheses with opposite signs. Square root 16 and square root 5. What's that? Oh, you're right. You're right. That one has the eyes. Don't do 4. I meant to miss that. I'm not requiring you guys to do that one. Alright, so let's look at 1 and 10, 1 through 10 on page 347. So you can cross out number 4 and 7. You don't have to do number 4 and 7. Skip 4, comma 7, not 4 through 7. Skip number 4 and 7. Oh, yeah. Yeah, yeah.